Okay. Now we'll do one more example with some more general setting. Here the independent variable is not x, it is t. Here omega is some constant which is non-negative, a positive constant. Non-negative is wrong, a positive constant. Again, there are two parts to the solution because this is a constant coefficient linear differential equation. So we need to find the complementary function first. You take the homogeneous equation where the right hand side is 0. Then you try this one as usual, but in the place of x, you have t now. K should be forced to be non-zero. So differentiate this. Now when you differentiate this, you can use this notation, right? Because dy by dt is y dot. Second derivative with respect to t is y double dot. Now, but you can, if you want, you can write dy by dt here and the second derivative of the usual notation here. You can do that still, it's okay. Now, you plug in the results in the equation and you can see that this is in fact the equation of a simple harmonic motion. Y double dot is equal to minus omega squared y. Okay, just keep that in your mind. So, pull out the common terms. So, you get this one. K is forced to be non-zero, this is non-zero, so you will end up with this one. So lambda squared is equal to minus omega squared. The square root of minus is plus or minus 1, sorry, plus or minus I, the square root of omega squared is omega. So here real part is 0, imaginary part is omega. So you can write the complementary function like e to the power alpha x, alpha t, times k1 cos omega t, sorry, beta t plus k2 sin beta t. In the place of beta, you plug in omega. So this is what you get as your complementary function. Now go for the particular integral. You consider the full equation. Now this is your regular trial because you have cos omega t. You try a cos omega t plus b sin omega t. However, these functions are in the complementary function as well. Therefore, this won't work because if you plug in this one in the left hand side, it will be vanished. It will be absorbed by the left hand side. Therefore, it won't produce anything to match with this one. Therefore, you multiply the regular choice by t. Why t? Because here you have to multiply it by the independent variable. Here t is the independent variable. In the previous examples, the independent variable was what? X. So you differentiate this. Right? A times the derivative of this is 1. Leave it as it is. Now do it in the other way around. A times t times the derivative of this minus omega sin omega t. Similarly, you differentiate it in the same fashion. Now gather the terms carrying cos omega t. So you have a plus b omega t. Again take these two. Sin omega t is common to these two. You have b minus a omega t here. Now differentiate this again. So you can differentiate this one b omega times cos omega t. Then leave this as it is and differentiate this one. Likewise, you know it's a product rule. You can do that. After that, you can gather common terms. Here, look, you have b omega cos omega t here. This is b omega cos omega t. So you can combine those two. You will get 2b omega cos omega t. Here you have minus a omega sin omega t. Here also you have minus a omega sin omega t. Those two will add up to this one. Now there are two more terms carrying t. So one is b omega squared. You can write omega squared first. Minus omega squared bt sin omega t. Minus omega squared at cos omega t. Now that's the second derivative. You don't need the first derivative. Therefore, you don't have to simplify that one. Now plug in the results. So from equation 2, from this one, you plug in this guy for y double dot, that is there, plus omega squared times y. This is your trial solution. You substitute that one. Now look, some terms will go away. As I told you, even though in this case, this multiplication of t facilitates us to do this, right? Once you substitute that result in the differential equation, the terms carrying t will go away. Look, There are 4 terms carrying t. This one, 1, 2, 3, 4. Look. Now what happens? Here you have omega squared at cos omega squared at sin cos omega t, but minus. So these two will go away. Similarly, this pair. So leaving, this guy is equal to 2 omega cos omega t. Now compare the coefficients of cos omega t. Here you have 2b omega, here you have 2 omega. So b is 1. If you do the same thing for sin omega t, you get a is equal to 0. So b is equal to 1. That means what? This is 1, this is 0. So you have t sin omega t as your particular integral. So that's why you have. Now write the complete primitive, the sum of these two, where k1 and k2 are arbitrary constants. Now let's have a little discussion on what happens here. In this example, the homogeneous equation is this. When you find the complementary function, this is what you got. So it simplifies this to this one. That means this is the characteristic equation of SHM, simple harmonic motion. Right? And we obtain the solution to this. It is this one. Both of them are oscillatory functions, and the natural frequency is omega, angular frequency. So omega is a natural frequency, of course angular frequency, but we'll call it as natural frequency. So it is omega. Now what happens here? Now this is the differential equation. You have a system, some system, we don't know what it is, but this differential equation describes that, that system. We don't know what it is. Some system, right? Now it is fed with cos omega t. What does that mean? Right? Let's go there and see what it is. Now you have some system. The system is described by that equation. This is the input. Say this may be an electric circuit and this is the input, or something like that. Here what happens is that the system has the natural frequency omega. You feed the system with the same frequency. Then what happens? Consider the case where k1 is equal to k2. What is the solution? Now, k1 and k2 are 0, but this is a complementary function. If you go for the particular integral, the complete primitive, these two are 0. I took 0 for the sake of simplicity. You can even put some values, but then there will be some algebra. You have to do some algebraic and trigonometric manipulations to write it as one function. So just to get rid of that, I can take these two as zeros. So this is what you get, t sin omega t. Y is k1 cos omega t. I should have erased that line. Hold on. I can, interchange these two. Complete primitive is more mathematical. In application sense, like you can write it as general solution. General solution is what? Y is equal to k1 cos omega t plus k2 sin omega t plus t sin omega t. Right? To make our life easier, let's take k1 is equal to 0. Let these two be equal to 0. So you get y is equal to t sin omega t. Now how do you sketch that? This, as I explained to you earlier, this gives you the envelope, this gives you the oscillation. So to determine the envelope, you first sketch y is equal to t. Then y is equal to minus t. Now the oscillation goes like this. It will never end. It will go on and on. It will increase like this. So what's the reason for this? Because the system has a natural frequency omega, and we feed the system with the same frequency. So system always gives you that, I mean, when it starts oscillation, we feed the same oscillation. So it goes on, and it will finally behave like this. So system probably cannot handle this oscillation, and it might collapse, right? This is called the resonance. The resonance takes place, so system may be blown up. And there's something happened a long time ago, nearly 80 years, in USA. It exactly happened in 1940. The bridge was constructed, I think, a few months back. And one day, there was a wind, right? It was not a hurricane or something, just a wind, like wind was blowing at 35 kilometers per mile, right? Almost just nothing. But the wind had this property, like it was like this. It was not blowing up at a constant speed. It was like this, it becomes faster then slower, faster, slower. The wind was not going in the other direction. It has the average 35, but it was like this. It was like that. Then what happened was, somehow this oscillation matched with the natural frequency of a certain bridge. That was, I think the bridge was in Washington. It's called Tacoma Bridge. It was the third largest suspension bridge at that time in the world. So what happened was, because of this wind, this oscillation, it meshed with the natural frequency of the bridge, right? Then it happens like this after that. It was simple, it started small oscillation like this. It's a huge road, right? It's a bridge road. So the road was going like this. Think about it. Then it kept going up, and finally what happens is, the structure cannot handle that oscillation. Finally it collapsed. But even though it's a very busy road, right? Fortunately, no human casualties. Only a dog died, but there was a person, some professor, who tried to save the dog. Somehow the professor just managed to save his life. You can see the video. We'll attach that video after this one. You can watch it. So sometimes that might happen. You have a certain natural frequency. You feed this system by the same frequency. So that's called the resonance. It goes on, and finally the system may collapse. Okay, thank you.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.